I now want to consider the idea of subspaces. We're going to start with a vector space V, and W is a subset of V. So W is contained in V. We then say W is a subspace if it is also a vector space under the same operations of V. So we have our vector space V, and we have vector addition and scalar multiplication defined on it. And if we can use those same operations on W and still get a vector space, then it's called a subspace. So it's kind of like a smaller vector space inside of the bigger one. However, we don't have to prove all 10 of our axioms for a subspace, since a lot of it will be inherited from the larger space. Instead, we need to prove 3 things. The first thing we need to prove is that the 0 vector is in W. So I need, at minimum, the 0 vector from V to also be in W. We need W to be closed under addition, so if I take 2 vectors in W and add them, I should still be in W. And we also need that W is closed under scalar multiplication, so multiplying by a scalar should not take me out of W either. So let's look at some examples of subspaces. I'm going to start by considering the set of all symmetric n by n matrices. We know all n by n matrices form a vector space, and so I want to see if the symmetric ones form a subspace. Well, the 0 matrix is definitely symmetric. So we take 0 transpose and we still get 0. So we have our first condition. Our second one, let's suppose A and B are symmetric. Then I need to prove that their sum is also symmetric. Well, A plus B transpose. We had previously talked about how we can distribute a transpose over addition, so this is A transpose plus B transpose. Since A is symmetric, A transpose is the same as A. Since B is symmetric, B transpose is B, and now I have the A plus B transpose is equal to A plus B. So A plus B is symmetric. The third one I want to look at is multiplying by a scalar. When we talked about transposes, I talked about how to distribute a transpose over a scalar multiplication, and it was just R times A transpose. Since A is symmetric, we know that A transpose is equal to A, so taking the transpose didn't change anything, and we have that this is still symmetric. So this would be a subspace. My next example, the set of all continuous functions on the interval minus infinity to infinity. This is denoted by C minus infinity infinity. And this one would be a subspace of my function space. In order to show this, my 0 function is my 0 vector, and we know this is a continuous function, since it is just a line and lines are continuous. So that's the first thing. The second thing, f plus g of x is equal to f of x plus g of x. And if f and g are both continuous, this is also continuous. So this is a theorem from calculus. And in addition, multiplying by a scalar gives me r times f of x. Also from calculus, we have a theorem that says this is also continuous. We don't change continuity when we multiply by a scalar. So this would be a subspace of my function space. The next one I want to consider is the set of all polynomials of degree 2. And this is actually not a subspace. First off, 0 does not have degree 2. So 0 is not in there. However, that's not the only thing. We can have a polynomial such as x squared plus 2x. This would be in there. We could also have a polynomial that said x squared minus 4. This is also degree 2. However, whenever I add these, I would get 2x minus 4, which is not degree 2. This is degree 1. So adding two polynomials of degree 2 does not give me a polynomial that's still degree 2. So this is not closed under addition. So not a subspace. So we're going to modify this slightly, the set of all polynomials of degree 2 or less. And this one is a subspace. And in this case, it's denoted by P2 since it's degree 2 or less. P3 would be degree 3 or less, etc. To actually prove this, we need to start with 0. 0 has degree 0, which is less than 2. If I have two polynomials of degree 2 or less and I add them up, well, the polynomial is still degree 2 or less. Like I showed in my last example, it could go down, but it will never go up. Adding two polynomials will not cause our degree to increase. In addition, r times a polynomial of degree 2 or less will still be degree 2 or less. Multiplying by a scalar will not change the degree at all. So this is a subspace. This time I'm going to let v1 and v2 be vectors in a vector space V, and h is equal to the span of these two vectors. And I want to show that h is a subspace. The first thing I need to show is that the 0 vector's in there. Well, we can write this as 0 times v1 plus 0 times v2. And this is in the span, it is in h, since it is a linear combination of my two vectors. I multiplied each one by a scalar and then added them up. For my second one, I need two vectors in the span. So I need a1 v1 plus a2 v2 and b1 v1 plus b2 v2. So this is what things look like in h. And then I need to look at adding them up. So I have a1 v1 plus a2 v2 plus b1 v1 plus b2 v2. I can regroup these. I'm going to write them as a1 plus b1 times v1 plus a2 plus b2 times v2. Well, this thing right here is in h, since I multiplied each vector by a scalar and then added them up. That is the definition of being in the span. The next one, I need to be able to multiply this vector, a1 v1 plus a2 v2, something in h, by r. That would give me ra1 times v1 plus ra2 times v2. And since each of these things here are just scalars, and I multiplied each vector by a scalar and added them up, this thing right here is in my span. So I've proven now that h has to be a subspace. And there's nothing unique here about two vectors. In general, if I have any set of vectors from a vector space V, the span of those vectors will be a subspace. I'm going to let h be the set of vectors of this form a plus 4b minus 7a plus b and 2a minus 3b, where a and b are arbitrary scalars. And I want to show that h is a subspace of R3. In order to do that, I'm going to start by writing this as an actual column matrix, so as a vector. A plus 4b minus 7a plus b and 2a minus 3b. I'm then going to break this up. I'm going to have my a terms, so I have an a minus 7a, and a 2a, plus my b terms, 4b, b minus 3b. Factoring out an a, I have a times 1 minus 7, 2. And factoring out a b, I have 4, 1 minus 3. Now if I call this vector v1 and this vector v2, since a and b are arbitrary numbers, this here, this thing right here, is a linear combination of v1 and v2. So that tells me H is really just the span of these two vectors that I defined as v1, v2. And that's enough, since I just showed that the span of any set of vectors is always a subspace of that vector space.